Welcome to a wide and quick chat from the Initiative in Computational Humanities, Arts, and the Social Sciences to the Faculty of Computing and Data Sciences at Boston University. Today we will hear from Professor Wesley Wildman, who is a professor of philosophy, theology, and ethics in the School of Theology and professor of computing and data science at the Faculty of Computing and Data Sciences. He will introduce for us computational policy simulation. Dr. Wildman's scholarly publications range from multidisciplinary comparative approaches in the philosophy of religion to computational policy analysis. He is executive director of the Center for Mind and Culture, a nonprofit research institute that employs computational simulation, data analytics, and other cutting-edge technologies to help solve pressing practical problems such as illegal child trafficking, social integration of immigrants and refugees, and religious radicalization. Please join me in welcoming Professor Wildman.
Lovely to be with you today. Thank you for coming. Let's talk about artificial societies for policy evaluation. It's a very powerful computational method that can be used to study all kinds of social problems, and in particular, the sorts of problems where policy interventions seem plausible or promising, and yet we're not really sure what would happen if we intervened. And we'd like to evaluate the policies in advance to make sure that we're making a good use of resources and money. We also want to affect the problem and not ignore it or choose policies that turn out to be irrelevant or even worsen the problem because of side effects. So, policy modelling matters. Policy impacts people, so policy professionals have explored every modelling modality as soon as it's stable and usable. The most common policy models are mathematical and economic, and they're used for making projections of measurable quantities and performing cost-benefit calculations. Computational simulation models use artificial societies. They're new modalities in the policy world, and policy people aren't completely used to them yet. In particular, they want to appraise their pros and cons carefully, so I'll be doing that in this quick talk today. And this type of modelling invites a participatory process. That means that despite the computational intensity of simulations, stakeholder involvement is really critical. You have to listen to figure out what elements need to be present in a computational social simulation. It's very easy to leave out a stakeholder perspective and come up with a policy that's effectively going to damage some people's interests, which could have been avoided if you'd listened more carefully at the start. And to listen carefully, you need to have the right people in the room. Now, I said policy professionals are curious, they're open-minded. There's a ton of different policy models. Institutional models and process models, rational models and incremental models. There are group models and elite models, public choice models and game theory models. What we're doing with computational policy simulation is introducing a new modality, which is quite general. It can be used to study all of those approaches in some way, but it uses very much computationally intensive methods. So what is policy simulation? It's a tool for strategic policy development. It can be used to test the impact of policies under many situations. So you can do what-if scenario analysis. What if this thing happened, then what would happen? Or what if these two policies came together, what would happen? Or what if these two policies were approved, funding failed for one, would the first one be able to continue? Would the effect be lost? So the procedure is that you're modelling a time-dependent process. It's very important to validate that computational simulation. You want to calibrate the simulation against real-world data. You want to test the simulation output against real-world data. And then you want to revise and retest until the simulation behaves like you know the world to be. And after that, you've gotten yourself an experimental platform, which is a virtual platform. You can experiment virtually. It's ethical to do that, as against experimenting on real people's lives, which could be death and life matters. You don't want to mess with people, so ethically it makes a lot of sense to do this in an artificial society. See what the effect of policy is. We use computational simulations all the time when we're building an airplane wing, when we're creating a factory or a distribution network. We're constantly building simulations because it's cheaper to try them out, to test them before you invest in them. We should be doing the same thing much more extensively with policy questions also. Now, the policy simulation process, those of you who know about policy will have seen this or something like it 1,000 times. You have to define a problem, you have to establish criteria for evaluation so that you can tell when your policy is performing well. You have to identify alternative policies and evaluate them. And then you have to display and distinguish among the alternatives to give yourself a reason for following one rather than another. Then you have to monitor the policy and feed data from monitoring back into the policy evaluation process. Policy simulation kicks in on those 4th and 5th steps right there. They help you evaluate alternative policies, and they display and distinguish among alternatives. They give you very helpful visualizations of the dynamics, the time-dependent development of policy effects, for example. And afterwards, when you're monitoring and implementing the policy, you can feed information back into the policy simulation, make tweaks, or sometimes just adjust parameters on the policy because now the real-world situation has changed, so you need your artificial society to be a little bit different than it was. Just a couple of quick examples of fairly famous policy simulations. One's called 1 Week. It's an online simulation game that enables policymakers to experience some of the challenges faced by people with limited resources just for 1 week out of their life. Now, distinguish between policy professionals, they're the experts who design models and analyse them, and policymakers who might be politicians who have to vote on things. One of the problems with politicians is that they're very busy and they may not have a deep understanding of a particular policy issue. Getting them to play a little simulation game like this gives them empathy for people who are affected by their own policies, and it makes them more mindful when they're considering policies and voting on them. And here's another example. Oregon discovered that there are a tremendous number of public assistance programs and tax credits, and how they interact with one another is just too complicated. Nobody can understand it. But the Oregon Enterprise Data Analytics platform creates simulations that allow people to select any combination of things that they do, from supplemental nutritional assistance programs or temporary assistance to needy families or employment-related daycare and so on. Put all of that stuff together, see what the effect is. Once you've got a model like that, you can run optimization experiments, asking questions such as, under what conditions do we maximize the amount of money that a poor family can bring in to support themselves? What combination of participation in policies would get that done? These are very important questions, and there's no other method to do that at the moment. Now, in our own lab, just to give you some more examples, policy simulation encourages generative social policy, including prediction of novel ideas for testing and evaluation. An example is in child sex trafficking, that if you end the prosecution of minors, which some states do, even though it's federally not allowed, you can drive down the demand for recruitment, which is an unexpected connection that dropped out of a computational policy simulation. So generative in the sense that it generates new ideas, new policy insights. And it forces conceptual clarity as well about assumptions, inferences, and consequences. An example is when you're trying to look at secularization processes, religion is a term that's not often defined very carefully. People's religiosity might have to do with whether or not they go to synagogue or church, might have to do with whether they pray or meditate, it might have to do with whether they give money, it might have to do whether they think it's personally important to them or their world of beliefs. It could mean anything. Synthesizing all of those things together into a coherent theory of religiosity and implementing that in a computational simulation not only connects more intimately to the relevant data, it makes the policy more relevant to actual people. It can allow for the integration of multiple policy relevant theories. It's very common when you're studying something like extremist violence to see a theory that's supposed to explain something. Someone else has another theory, and the two theories operate as competitors in the marketplace of ideas. Whereas in fact they're often not actually competitive. Quite often they're perspectively related to one another. integrating those theories in an appropriate way is something that you can do and then demonstrate that the integration is coherent by implementing it in a computational system, which is a fairly strong constraint on coherence. You can also empirically ground policy simulations in very strong ways. And we did that with COVID forensics, for example, using computational policy simulations to investigate the reasons why universities who published their daily testing results had the pattern of testing that they had, the COVID positivity rates. We were able to tell, for example, precisely when there was an illegitimate party that was thrown. This level of sophisticated control over empirical details is not usually possible in policy simulation. You can also shift the burden of proof in complex policy debates. If picture a policy room where there's one big heavyweight who thinks this is what you should do, and some newcomer who says, no, we should try something else. And look, I've got this policy simulation that explains why you should try this other thing. You run the policy, it's making a case and shifting the burden of proof. So now that heavyweight policy professional has to argue against what's been said or produce their own policy simulation to demonstrate why their ideas should be listened to. So it's a democratizing influence in the policy rooms, which are complicated and often hierarchical and power complex places. It can change the tone and methods of strategic discussions by including stakeholders, by getting breakthroughs in areas where we feel stuck. Like we study rural suicide. It's very common to feel helpless in the face of a problem like that. So much money being thrown at this problem, and yet suicide rates continue to increase. So we need some type of breakthrough. Can simulation help with that? You can combine your deep compassion for people in pain with high-level computational methods that actually might give you a shot at making a difference. And finally, it can help with disaster management, rethinking resource deployment, avoiding disasters. Military groups routinely use policy simulation to map out battles, encounters in military space. That includes the provision of resources, where the equipment is, where the expertise is, how communication is working, anticipating moves of enemies. It's all handled in computational social simulations like this. The very same thing can be used to handle disasters like dam breaks, which have happened in this country at times, or other things. So what can policy simulation achieve at present? Well, we have to be humble here. Almost all complex social situations have been unpredictable. They routinely defeat modelling efforts. And to the extent that policy simulation is expected to predict precisely in order to evaluate policy options, that means there's going to be a serious problem. It becomes relevant when social complexity makes simpler modelling approaches untenable, but it routinely involves assumptions, and there's very often insufficient evidence for them. And in this modelling modality, there's often a ton of assumptions, small ones, but a lot of them, having to do with how you measure things or how you implement parameters in the mathematics of a simulation. So policy simulation might be necessary, driven to necessity by the complexity of social life, but it's not thereby sufficient for producing accurate policy predictions. So that's important, and it's just as well in that policy simulation has other uses besides prediction. It generates insights because it forces conceptual clarification much more efficiently than other methods. It detects possibilities. Even if accurate predictions challenging entire regimes of a model's behaviour can point to possibilities for policy exploration that haven't come up in the debates. It's good at estimating uncertainty, not just giving you a line of action, but telling you how likely it's like to work, what the probability envelope around that particular strategy might be. And it identifies policy levers. And using sensitivity analysis, you can see which policy levers are most likely to be most effective and how they interact with each other and so on. So all of these uses of policy simulation are important and valuable even when accurate prediction remains out of reach. Now let's talk about ethics for a minute. We need to get much better at ethical analysis of the assumptions and limitations that are built into these simulations. Policy simulations often make ethically charged assumptions. Just ask a stakeholder about a policy that was implemented by a state government or something. Ask them how they feel about the policy. And very often, a neglected stakeholder is going to say they never talked to us about it. So there's assumptions that are built into the way these things work. And unless you're using a participatory modelling process and talking to the right people who have a stake, you're going to wind up just reproducing the ignorance or the bias that you see in the rest of the policy field. Just because you've got a more powerful tool doesn't help unless people are listening to the correct stakeholders. And they always encode design assumptions. Subject matter experts can help us figure out where the weak points are, where the vulnerabilities to assumptions lie. And that's on the assumptions and limitations side, but we also need to get better at ethical analysis of the implications and applications of policy simulations. They can be used to support ethically questionable actions. If you want to know what the best way is to silence a group of protesters, you can use a policy simulation to do that. Policy simulations are neutral, equal opportunity tools, and you can use them for good and for evil, just like pretty much any other computational method that you can think of. So you need to be ethically mindful of the way you use these things. They also require training on the policy side, because there are limitations in every simulation, and if someone gets excited about being able to use a simulation, they might fail to convey that forwards to the people who are going to continue to use the simulation. So from designers to users, there can be a gap, and maybe several steps of gap, which make it very difficult for people to have a responsible concept of what the simulation's good for and what it's not. So ethical management of the risks and dangers of policy simulation critically requires teamwork across relevant stakeholders, designers, and policy experts. So to wrap up, policy simulation is a social science method that works naturally with both qualitative and quantitative data, requires multidisciplinary, problem-focused cooperation, capitalizes on and encourages stakeholder engagement, improves chances of research funding applications, and don't forget about that. It increases the impact of research. And a policy simulation exercise does not require you to be a programmer. Policy professionals and policy researchers typically team up with engineers and data scientists to create policy simulations. Chaz and the Faculty of Computing and Data Sciences may be able to help you make connections with engineers and research groups that build policy simulations. So you bring the subject matter expertise, the data, the research questions, and the engineers can help bring your vision to reality at the level of a project proposal, fundraising proposal, at the level of publications, and so on. And there's an option too if you want to take a class. Professor Andrew Bell in the College of Arts and Sciences Earth and Environment Department is routinely now teaching a course in agent-based modelling, which is the right kind of simulation technique for building artificial societies. So you can get into it through coursework as well. If you've got other questions about how to pursue getting into this kind of thing, there are other resources, and in due course they'll be on the Chaz website, so that's bu.edu/CHASS. Thank you for your attention. Do we have any questions?
Yeah, like take a really complex problem like recent bank failures and like wondering why, like there's all these like monetary management policies that lots of people argue about whether or not if these are the reasons for these bank failures or not. You could also ask the question about like, why is it this strange triangle in the insurance world and healthcare? Why is this strange triangle between the government, insurance companies, and health providers somehow creating this pattern of high costs and low quality service? Like, I think maybe, I don't know if these problems are good examples of very complex examples, but they seem to be good examples like that to me? And like, what are the big barriers to being able to use this kind of method to model policies in these kinds of very complex situations?
Thanks for the question, Tate. Yeah, we really want to know why things happen, in particular why they go wrong. This really matters to us. So this is a question of causal inference. The unique character of these computational social simulations is that they are causal models. That's very important. So very often when we're modeling, for example, if we're using linear regression, we're taking a real world situation, we're looking for relationships, we build a linear regression model and we figure we're discovering something about those relationships. But that's not guaranteeing anything about causation. You don't get causal information from a regression straightforwardly. But these are models where the causal architecture of the model is supposed to mirror the causal architecture in the world. So you've got a much better shot at supporting strong causal inference and understanding answers to the question how a policy shift would make a difference. So on those bank failures, did the weakening of the regulations really make the difference or not? So if you set up a computational simulation where one of the parameters is the strength of those regulations with regard, for example, to how much cash you need to have on hand, if that's one of those parameters and there are 10 other parameters, you do a sensitivity analysis and you see on what the outcomes really depend. It could be that you thought that was the issue, but there's some other parameter down there that makes a bigger difference. And you've got confidence in that system because you've validated the causal architecture of the model so that you felt like it was mirroring the real world causal process. This is what makes this such a revolutionary way of approaching social policy matters.
Hi, Dr. Wildman. I was curious, is this model only applying to the macro level, like public policy? But when it comes to policy within an organization or institute, would this model apply like a micro level?
Yes, good question. This is an equal opportunity system. You can probably sense from the way it's set up, it doesn't depend on any particular level. What you're doing is using individual agents who represent something, sometimes groups, sometimes people, sometimes companies, sometimes vehicles, doesn't really matter what it is. In this case, they could be people and relationships between people so that they're communicating or behaving in response to what other people do. And if they've got individual characteristics such as personality, they may behave differently than someone else would to the very same inputs or the very same environmental conditions. And those interactions between people, when constrained by social environments and pressures, emerge into system-level behaviours. That's the general principle of one of these models, and that can happen at a very small level inside a community, inside a company, or inside a whole nation, or indeed global simulations that are attempting to explain the way misinformation spreads around the entire world. So yeah, extremely flexible methodologies. The challenge in return is that it can be difficult to have the data needed to validate such models. So very often you pursue models when the data exists to give you most confidence in their validity.
What's the size? What are the smaller size, like, to even be able to run the test?
So we've run computational policy simulations on small groups of people, just like 50 to 100 people, usually to test something larger. It's more common to run them on the size of, say, a small town where you can get more complex emergent features. But you can go very large. These days people have got the computational resources and system engineering facilities to be able to support millions and millions and even billions of agents with very complicated exchange relationships between them and subtle machine learning style characteristics within each agent so that they can learn from their environments and learn from their interactions with other people. For example, they have memory and they learn who to trust and who not to trust. So that means that these are extremely highly parameterized models with a tremendous amount of variables that can constrain their behavior. Consequently, validation becomes extra challenging. You need data to calibrate those models against every single one of those parameters that you might think. One little comment on that. Fortunately, when you don't know a parameter, you can parameterize your uncertainty and make a prediction about what the data set should be and fiddle around with that parameter to calibrate the model in such a way that the model lands on the behavior that you're seeing in the real world. And at that point, you're making a prediction about the data. If people collected data, this is what they would find. And that, of course, can be evaluated.
Thank you.
Do you happen to have on the top of your head maybe a couple of like the flagship success stories of where this method was able to beat that complexity of the world and like actually have validated predictions that were eventually validated as having gotten it right?
Yeah. There's a thing out there called mutually escalating religious violence. You will have seen this in Protestants versus Catholics, in Northern Ireland, in Hindus versus Muslims, in the Gujarat riots and the aftermath in India. So there's a number of places where this has happened. One group does something against a background of resentment. There's a sharp response that causes a sharp response, and you get mutually escalating religious violence. So we were quite interested as a research group in making sure that we understood why this was happening so that we could propose policies that might make it less likely. And in the process, we came up with a computational simulation that could predict the occurrence of mutually escalating religious violence significantly better, many times better than any of the other existing models, including regression models and game theoretic models and everything else. So these are hard constraints to match when you've got an actual timeline of mutual escalating violence that you have to hit. And being able to do it accurately was a real triumph for this method. And it also led to policy suggestions, like when do you need to be careful and when don't you need to worry about it? When are the danger signs, in other words? And the papers describing this specify what those danger signs are.